Hi, I am just piloting an idea for a sort of web show called New Furrows. The idea is that I'm a doctor of inorganic chemistry and I know some chemistry, but I've been out of it for a little bit. So what I thought I'd do is just read the journals for a bit, and I'll explain the type. Probably I'll just read the titles and explain what's happening at the moment. I'm at the point where I just need to know what the landscape is before I even start reading properly. So, what we've got here is Inorg Chem. It's about inorganic chemistry, which is one of the three areas of chemistry. There's organic, inorganic, physical. And of course, then it gets even more interesting, like the nanoscience, all that stuff. Like, there are strata. But inorganic chemistry is mostly about metals and non all of the periodic table, not just carbon and covalently made molecules, which tend to be more prevalent in like medicinal chemistry and stuff like that. Though there are inorganic medicines, and that's what I kind of learned about in the group that I work with. So I'm looking at inorganic chem here. We're looking at the whole periodic table, so anything can kind of show up in here. But what it's probably not going to be is, oh, this is how you make Olrexrent or some random drug. And I should say what inorganic is then. So it's kind of at the top level of the the strata, and there's like European Journal and all sorts of different magazines that are higher and higher and higher, and then you get Science and Nature at the top that are basically like headline, like we've found life here stuff that like all scientists need to know. Right up at the top. But then, in all chem, it's a good journal. It's a nice journal. I liked it a lot. So, let's have a look. So it starts off with like an editorial discussion about like what is science at the moment. And, at the moment they're very political, which makes complete sense. It's all about equity and diversity, and, universities need to work on it, and they are, to some degree. Yeah. So, cool. So let's get to the articles. I'm just going to read a few. Okay, cool. Selective and efficient biomacromolecular extraction of rare earth elements using land moduling. So rare earth elements are at the bottom of the periodic table. There's like a periodic table, and there's a little bit hanging out at the bottom there. The lanthanides and the actinides. They are actually not as rare as you think, and the one that you're mostly used to is probably neodymium magnets, stuff like that. So they're all metals. And metals are cool because they're not very limited in structure. You can have all sorts of different shapes of metals. By that I mean how they bond with each other. So like here, this is one shape that a molecule could have, but there's millions. And so the connection shapes are all really interesting. But lanthanides down there in the rare earth elements just can make lots and lots of bonds as well, so they have really great shapes. So that's as far as I'm going with that. I'm just defining a few terms and then get further. Aqueous stability and ligand substitution. A ligand is an organic fragment attached to a metal. Ligand substitution is switching one thing for another. The reason that's useful is because once you get metals with ligands around them, it's a bit like building a little machine. You can change the structure. A really common one would be like the Ziegler-Natta catalyst, right? It gets ethene molecules, little tiny 2 carbon molecules. I won't build a model. 2 carbon molecules, and it just puts them together, and that's all it does. And it does that with basically clouds of electrons, like being in the right place at the right time to pop apart bonds and put them all together again. So ligands are what shapes the metal to do what you want it to do, and not just oxidize to something. They block the metal off, and they keep it, in whatever the steric and electronic environments are, steric shape, electronic natures of the electrons, position they need to be in. Most of the time, for metals, when they are doing a reaction, they want to be very electron poor. Most of the time, the molecule is coming in, joining to the metal, using its electrons, and then then being changed while it's there. So quite often you want a metal that's poor in electrons to attract that thing over. So the ligands can help you with that. They can remove electron density or donate electron density. They can again change the shapes, the sterics of it, and all that stuff. Sterics are important because the bigger, for instance, the bigger the reactive face we call it, is the metal, the area that other things can attach to, the more molecules it can get to, but then the smaller, the more limited it is. In lots of different ways, sterically and electronically. So, how far did I get? Aqueous stability, how stable something is in water, and ligand substitution of. So they're about to tell us about a complex of some form, and that's how this is worded. So they are substituting the ligand on this thing, a layered copper-1 isocyanide. Isocyanides are kind of like nitrogen-y containing ligands, so really donating of electrons. Based organometallic, made of metals and carbon chains. That usually means like alkyl carbon chains, like petrol. that might make sense to you, or it might not. Organometallic network material, so a material that forms a specific shape that allows it to do certain things. So, for instance, a moth, which probably I'm just describing the general term here. A metal organic framework has pockets for gases or something like that to occupy. So if you don't want to store cylinders of hydrogen in a car, for instance, you want to absorb it to something with a giganto surface, and these are if you imagine a sponge, but where the connecting bits are just atoms thick, and so there's just an incredible amount of space in them. With a well-defined channel structure, great. So it might be that you want to pass a certain ion through it. You only want to allow protons through it, or you only want to allow really electron-dense things through it. That is why you would start to change the shape. So again, we're talking about a really nice crystal structure, and also crystals. Like crystals, I could talk about crystals forever, but let's not. Okay, I'll just read a couple more, and then I'm done. 2-step thermo-induced metal-to-metal electron transfer. So I think that makes sense on its own. And on-off photo switching in a molecular iron cobalt complex. Cool. So, thermo-induced metal-to-metal electron transfer means you provide energy. You provide energy to a substance, and that energy will be used to transfer electrons from one substance to another, therefore changing some property about it. Its colour, some frequency that it absorbs or emits. What other things? Magnetics is going to be like your major thing there. Some complexes, when they have certain numbers of electrons, become magnetic and then not magnetic. So this is perhaps thinking about data storage and things like that, pluses and minuses. And it's talking about a square complex, which, again, crystals, I could talk about them forever. Did I say one more? What are we on? 8 minutes. Okay, I'll just one more. But I do not know anything about radioactive chemistry, so now I'm going to go through and see things that I think I might know about. Ooh, taxanes, they're fun. But do I care about them? Yes. Yeah. Ooh. Synthesis of... Okay, no. I'll be done there. That's it. I don't know if that's interesting or not.